Hello, welcome back to Stochastic Processes class. My name is Sonny from Godobi, and I'll be taking through this. So today we'll be checking Chapman Kolmogorov equation. In our previous lesson, we shared the two-step transition probabilities, and then we are going to continue from the two-step transition probabilities. So we find out that our two-step probability of moving from state I to state J over t-step. So we have it as period power 3, the probability of moving to state J over t-step, given that our current state, which is not, is equals to I. So it's given as that. So but however, this will not help us enough by the time we have a higher number of steps to check. But by the help of Chapman Kolmogorov equation that we are going to study today, we should be able to have a better understanding and going to ease you in calculation that have to do with over steps. Alright, so let's assume that we have a state here and we have another state here. So this is my current state I, and this is the state I'm going, which is state J, and that is over n step from here to here. I have n step, but however I can partition it. I can partition it to 2, and say from here to here I have k. So from here to here I have k from my current state to the point I partition it k, then from my partition state to where I'm going, that will be j. Is that taken? Alright, so let's see how we can derive this equation. So the Kolmogorov equation is given as the probability of moving from state I to state J over n step, in this way, is given as summation of k, where k belongs to the state samples, the probability of moving to state n over state J, given that your current state is I, is given as summation to state space P of I k R, then P of kj n minus R. Alright, so we'll first of all prove this Chapman Kolmogorov equation here. This is Chapman Kolmogorov equation. In our next video, we are going to see how it works. We'll use it to solve some couples of questions. So let's begin the proof. We have so following our previous way of proving over step 2 over step 3 and over n step, you can watch our previous video to see how we actually check that. We had the probability of moving from state I to state J over n step. You see that probability of moving from state I to state J over n step. So we can partition it as probability of moving from state I to state n to J, given that our movement is from state I to K, so we take that as R. Okay, state R equals to our K over R step, rather we take it from here to here, that's over R step to K. Then since we partition, we have to bring it out, probability of I, we have to bring this out, X index R equals to K. Is using partition theorem. You can check our previous video for better understanding of this method, and this is the simplest method I believe so far. So this equals to probability of, so we can bring in our current state I, that will be xn equals to g, given that our partition state over R is k, x naught is equals to I equals to p x r equals to k, given that our current state is equals to I. So applying the Markov property that said that it all matters where you are and not where you have been. Markov property, this don't forget, this our future state, this our current state, and this is a previous state. So and Markov saying that for us to predict the future state, we only need the current state and not the previous state. So implement that property this way. That we go, then we are going to have probability of moving to next state j over n step, given that xr equals to k, probability of xr equals to k, given that x naught equals to I. Here we implement Markov property. Okay. Oh, sorry, I have excluded my summation. Pardon for that. Summation k not to the state space. Since I've introduced k here, and then I'm supposed to include this my summation sign. Sorry for that. Here. So here. Then I want to rewrite this using my matrix notation. Then I have probability of k to j, and that is over n minus r, and probability of moving from I to k, and that is from r minus 0, which is r. So I can actually rewrite this table of empty set by this phrase, that's probability of I k r and probability of k to j over n minus r. Okay, so you can see that that's actually equals to the probability of moving from I to j over n step is equals to summation of k belongs to the state space. Then we have p I k partition into r, then p k to j to n minus r. So this are Chapman Kolmogorov equation, which is called CK equation. So in our next video, we will see how to actually implement this particular equation and see that it's actually good in solving this step transition probability. Thank you for watching. See you in the next video.